All right, in this video, we're going to be talking about section 6.3, which is about vectors in a plane. So before we get into what vectors are, let's take a few minutes and remind ourselves what the distance formula is between 2 points. All right, so when we look at our graph, that's not very straight, but we're going to roll with it. And we have 2 points. Let's just kind of give this point right here. We'll call this x2, y2. And let's call another point, like let's call this one right here. Let's call that x1, y1. And I want to know the distance between those points. Well, the simple way of doing this is to not visualize a straight line, but to visualize it as the hypotenuse of a right triangle. And so if we take a look at, I'm not drawing straight lines today. If we take a look at this triangle, we see that the hypotenuse is, in fact, the distance. So we're looking for this D. And so how are we going to find the distance, this length of this leg? This, of course, would be the height of the highest one minus the smallest one. And this one would be the biggest one minus the smallest one. And so those are the distance of the two legs. So that means we're left with d squared, using the Pythagorean theorem, of x2 minus x1 squared. So a squared plus b squared, which is y2 minus y1 squared. And so d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And of course, there are going to be a couple of you that are going to desperately want to just make the square root go away and make the squares go away, but that would be doing a square root term by term, and we know we don't do functions that way. So this is the distance formula, which, I have memorized, but I never really think about. I always just think about it being the Pythagorean theorem. So hopefully this is something that is easy for you. All right, so let's look at a couple definitions. Today we're going to be talking about a vector. A vector, and the symbol for a vector, as you can see there, the name of the vector is A to B, where we're going from A to B, and that's why the little half arrowhead is pointing that direction. It's an object that has both magnitude and direction. So a vector, the length matters. The magnitude of it, meaning how big it is, how long it is, as well as its direction. Geometrically, we represent a vector as a directed line segment that has a magnitude. The length, the magnitude of the vector is indicated with these double absolute value symbols. So that's the length of the vector, an arrow indicating the direction. The direction of the vector is from its initial point or tail to the terminal point or the head. So how is this the same as a ray? How is it different than a ray? Well, if I were to draw from this point right here and draw a ray through this point, a ray goes on infinitely long, right? So it has no magnitude because its magnitude is infinity. When we're talking about the difference between a ray and a vector, we actually are talking about heading from this point to this point. The direction would be the same as that ray, but the magnitude is only the distance between them. So when we're talking about a vector, we're talking about not only the direction, but we're also talking about the length of that directed line segment. Okay? A line segment, the direction doesn't matter, right? We could either go this way or this way, so that's why that's not a vector. We call it a directed line segment because we start here and maybe go to here, or maybe we go the other way. So the direction matters, as well as the length. So that's how it's different from a ray and a line segment. It's kind of a combo of the two. All right, so let's take a look. Example number 1. Given A equals 2, 4 and B equals 5, 8, graph the vector A to B. So 2, 4, here's the point A. B, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Of course, I've made it too big. We're going to estimate there is B. So me graphing the vector starting at the terminal point A, the tail, and going to the head at B. So there's the vector we're talking about. And now the question is part B. Remember, this symbol means magnitude or its length. Magnitude. So we're going to need to do the distance formula. Or in other words, again, think about it as being a right triangle and you're just finding the hypotenuse. And so the distance formula equals the square root of x minus x. Now, it doesn't matter which one you do, 2 minus 5 or 5 minus 2, although one would be negative, one would be positive, because the next thing I'm going to do is square it. So either way, it'll turn out positive. Plus, and then 4 minus 8 squared. So the distance equals the square root of negative 3 squared is 9, plus 4 minus 8 is 4. That's 16. So my distance equals the square root of 25, which is a distance of 5. So 5. All right. Now, part C. Draw a vector with an initial point 0, 0 that is equivalent to AB, the one we just did, on the same graph. All right, so this brings up a point, is a vector has magnitude and direction, but where it starts and ends is flexible. So we can say two vectors are equivalent if they are going the same direction and they have the same length. So if we take a look at what we did here, we had a vector that went over how many? 3 and up 4. And that gave a magnitude of 5. So if we start at 0, 0, we can duplicate this vector by simply 1, 2, 3, 1, 2, 3, 4. So here is like A prime. Kind of missed my point a little bit. And that would be B prime. And that vector, A prime, B prime, would be the exact same vector as AB. Just started at a different spot. Which brings us to the definition we see highlighted below. Two vectors are considered equivalent if they have the same direction and magnitude. All right, moving on. We're going to kind of go through this pretty quick because it's a pretty easy concept. Definition, another way you can talk about vectors instead of where do they start and where do they end, is we can talk about what's known as the component form of a vector. That gives you the coordinates of the terminal point, and we are assuming that the initial point is the origin. Okay, so let's take a look at what that means. All right, so this is the notation for component form. Graph each vector. So we're going to graph vector u, right? So there's the symbol for a vector right there. And again, we have these little triangle, these little angled pieces. That is what tells you it's a component form. And what this is telling you essentially the horizontal component and the vertical component. So keep in mind, you can start and end a vector wherever you want. When we're doing component form, we're basically making the assumption that we're starting at 0, 0. So if my horizontal component is 3, 1, 2, 3, and then negative 2, then we have the vector right here. We went over 3, we went down 2, and the vector is, again, the hypotenuse of that triangle that is formed. So this is vector u. Vector v will graph also from 0, 0, negative 1, 5. So we're going to go over 1 in the negative direction, and 1, 2, 3, 4, 5. So our vector v would be this vector represented here. Okay. So the component form is a very simple way of talking about a vector Because again, while we're assuming it starts at 0, 0, remember the definition of a vector is we don't technically care where it starts and ends. We care about direction and magnitude. So technically speaking, we could draw a vector u by, starting here and going over 1 and up 5, making the same, vector right there. Okay. Now let's look at part B. Let's do some addition with vectors u and v. So when we add vectors together, it's very simple. What we do is we can, first of all, represent this graphically. Remember, vector v that we drew here doesn't really have to start at 0, 0. It can start wherever we want it to. So what we're going to do is we're going to take vector v and just slide it over and put the tail of vector v at the head of vector u. So in other words, I'm going to start vector v right here. So I'm going to go over, it was negative 1, 5. So I'm going to go over 1, 1, 2, 3, 4, 5. So I could copy vector v to be here. Or I could have taken vector u, if I had done vector v first, this red line, then I could take the tail of u and start it at the head of v. So that vector, vector u is over 3 and down 2. 1, 2, 3, 1, 2. Notice that puts me at the same spot. So the sum of two vectors is in fact going to be this vector right here. It is the resultant vector. So the answer would be 1, 2, 1, 2, 3. So this is the vector 2, 3. Okay, so it's the diagonal of the parallelogram that gets formed when you put those two vectors together. So that's the answer graphically. If you want to find the answer just mathematically, then it is just as simple as adding the different components together. So if I want to add vectors u and v together, then u plus v is simply going to be 3, negative 2 plus negative 1, 5. And what we're going to do is we're going to add the component forms together. So it may make it more sense to like put them next to each other, like underneath or something. But essentially, I'm going to do 3 and negative 1, which makes 2, and negative 2 and 5, which makes 3. And notice we got the same answer here as we did right here. So we can do it graphically, making the parallelogram. And we're looking at the diagonal there. Or we can just simply add the components together. Add the horizontal and vertical components together. And again, that could be misleading. I'm not saying add the x and the y. I'm saying add the x's and add the y's. The x plus x and the y plus the y. All right. And this is what's known as, again, as the resultant vector. Okay, so that is our introduction to vectors. And we'll do a little bit more with them in the next lesson.